Now we're recording, okay? And let me do my screen share for the book. Can everyone see the book now? All right, good deal. Let me move my taskbar out of the way because it's blocking the book. And I'll move James out of the way because he's blocking part of the book. But didn't get him far enough out of the way. There we go. All right, now I ask again, any questions, comments, anything to bring up before we get going today? I think all of you except Ryan was probably in my last class, and in that class I found an interesting question right at the end of class. I had said I put the Chapter 8 test out there for them on Blackboard message, and he said on his, one of the students said on his phone he couldn't get Blackboard message to open and stuff, so I moved it. Well, I didn't move it, I just opened it, put it in another place under weekly assessment. I put the test there. Now I believe I put your test also out there, didn't I? Does anyone check to see Blackboard, what you call it, message? I can't remember if I put your test out there or not. Did anyone check? Okay. Can everyone get to the messages to get the test? Anyone who cannot? Okay. Well, then I'll leave it there, but if you can't get to it, let me know, and I'll also put it under week 4 assessment. Okay. I can put it either place. I can put it both places. But I was surprised to learn that a student who had been in my class last summer and never had any problem getting it now couldn't. But I understand some people's computers aren't doing as well as they were or whatever. So he was having to use his phone and he couldn't get it through his phone. Okay. Now Ryan, I see you've got your video on. Can you hear me okay or not?
Yes, sir. We are good.
Okay. When I told my wife what happened last week, she said, well, sometimes the bandwidth is not strong enough to support video and audio. So if it gets so you can't understand me well on the audio, turn off the video and that should make the audio a little bit better. Make sense?
Yes, sir.
Because she, in a meeting she was in last week, same day that we were here on Wednesday, and I told her about it. She said same thing happened to her, so she just turned off her video and she could hear better then. So if that ever happens again, give that a shot. All right, any other issues, concerns, problems? I don't know if y'all were waiting around as long as I was, but Zoom would not connect. My first 2 classes connected no problem. Yesterday 4 classes connected no problem. Generally they've been doing quite well last week, but this class today would not connect. I tried it twice the way we were before, then shut that down, brought Zoom back up, still would not connect. So then I had to take everything down, shut down everything on my computer and turn the computer off, and then turn it back on again. And then I sat for quite a while. Well, the first time it wouldn't even get into Zoom, and so I tried it one more time that way. It did get in, then tried to connect, and even then took a long time. So I've been here since before 2:30 trying to get Zoom to connect. It just now, you know, when it did. All right, where we left off last time, we're on page 28, as you see in front of you there. We're talking about suspended cables. Again, these are applications of differential equations and or using differential equations as mathematical models. Now, I don't know if you've ever noticed it or not. I'm looking out my window now, and I can see the wires coming from the power pole to the house, from the power pole to the neighbor's house, from the one power pole to another power pole. All of them have this sag in them. Now, doesn't that seem like they were wasting cable there? Why didn't they string it up pretty tight, and therefore they wouldn't have had to run as much cable? You think that would work? Why not? It is. You're absolutely right. There's always going to be some pull. If they were out there in the middle of summertime running these things and did them just as tight as they possibly could, and then left them next winter, it would have popped the power poles or broken the wires one, because the wires have enough of that coefficient of linear expansion and contraction that if you ran them in the heat of the summer and did them as tightly as you could, then in the wintertime they would either pop the cable or break the pole. Literally, they could break the power pole because it's that much. So yeah, you've got to have a sag in it, and it'll be a greater sag in the summertime here because the cables have expanded, and in the wintertime the sag, if you notice it, it will be a little bit less, but there will always be a sag, just as Ryan said, because gravity is always pulling down on it. So if we're trying to model this, what you have is a tension in one direction and a tension in the other direction. And they just happen to pick one place location down here at 0A, which is low as that cable will ever go, and the other one up here at some arbitrary place here. And then they set up the equations for the T1 in this direction, T2 cosine theta here, T2 sine theta here, and the pull of gravity here, weight here. Those are the tensions on them. And then your dy dx, that's the change of y per change of x, okay? That's equal, these T1 cosine theta and T1 and T2 cosine theta, they have to exactly balance. The wires aren't going left or right anywhere. They're only potentially going up and down. So the dy dx, the only movement that you'll have here is the ratio of the weight downward to the tension upward, which is, wait a minute, they have, no, I'm sorry. This is the T1, okay, sorry, I said that. They still don't have this set up properly, I don't think, okay? T1 is equal to T2, yeah, T1 is equal to T2 cosine theta, and here the weight, it has to be equal to T2 sine theta. That's correct. By dividing this equation with by that equation, you see what you get. You eliminate the T2s, and then you get the dy dx. Well, let's see, somewhere up here I don't see where they said it, but dy dx is basically tangent theta. And what is tangent theta? Sine theta over cosine theta. So that will give you the dy dx is w over t1. Everything else falls apart. Well, there is your differential equation. There's your derivative, and there's your what the derivative is equal to, w over t1. Now, used to doing slideshows, and I just hit to advance the slide. There aren't any slides. Okay. Now, there's a simple first order differential equation as a model for both shape of a flexible wire, such as a telephone wire, a bridge, the suspension cable on a bridge. Same type deal. Okay, same type deal here. Okay, There, the weight is more than W downward. It's the weight of the things underneath it. So it's a little more complicated problem, but the problem is the same. Now, they say here what lies ahead. Throughout the text, you'll see three different types of approaches to or analyses of differential equations. Okay? And here are those three. The first is your analytical approach. That's what we've been doing, well, kind of getting ready for anyway, so far. Once you've done that, then you can do a qualitative analysis, okay? And then a third way is numerical analysis. The sad news is most of our calculations will be in real life, will probably be numerical, because you have to have a very solvable differential equation to do the analytical approach. The qualitative analysis just lets you know, that's kind of like the direction fields and those kind of things. That it gives you a qualitative feel for what's going on, but in reality, most of the time you'll be doing probably a numerical analysis, if and when you ever have to do them. Okay, a lot of engineers will probably claim they've never solved a differential equation since they left college, and maybe some of them that's true, but in general, this gives you an idea of what's going on with them, and we'll go from there. So let's move on to the remarks. Okay, here is the analytical, or at least an illustration of that approach when you're working everything out. The qualitative is just getting an idea of what things are happening, and then numerical is letting a finite difference or finite there's another name I can't remember, technique for solving differential equations. That is just about the end of chapter 1. Okay, here are a few remarks. In each example in this section, described a dynamical system, a system that involves a flow of time t. More precise term, a dynamical system consists of a set of time-dependent variables, often called the state variables. Now, whether you run into these terminologies again, I don't know. My guess is you probably will. If you do, you've heard them before. Here they are. Now, the state of a system at any time t is when you plug that time t into your time-dependent variables. Okay, in other words, plug in the time you're dealing with, and that will determine what the state variables are. The solution of your initial value problem is sometimes referred to as the response of the system to the conditions that you put it under, those initial values. Okay, not going to do a whole lot here, just showing you some of the key words. You'll probably run into them again. I don't know how much of this you'll get into in statics and dynamics, but it seems like dynamics would certainly have something to do with these kind of things. So homework exercises here, I think I gave most of these to you before. If you want to go back and do population dynamics, you can do either problems 1 or 3. If you want to do Newton's law of cooling or warming, that would be 5, I think, is the only one there. Let me be easier for me to look at the page. Yeah, only one there. Then of the odd number problem. Now this is only if you can find the answers in the back. If you can't, the spread of a disease or technology, or that means disease in technology like a computer virus or something, that's number 7. The mixtures problem will either be 9 or 11. Okay, there's question 9 and there's question 11. Then the draining a tank, that's going to be 13. Your series circuits is, I think, only 15. Falling objects, they love doing Einstein looking figures, don't they? That would be 17. That includes air resistance. um, Newton's second law and Hooke's law, sort of a combination of those. That would be number 19 on the next page, right there. Newton's second law, variable mass, that would be rocketry basically. That's number 21. And Newton's law, second law and universal gravitation, that would be 23 that you see on the same slide here. Okay. Now they do have a few additional models that we probably didn't talk about to much detail. And if you want to try some of those, you certainly can. These should have answers in the back. Any of the odds, 25, either 25 or 25 through 29. There's 25, 27, or 29. Right there, reflecting surface. Again, you don't have to do those, but if you want to give them a shot, if that's going to be something that looks like you might be doing in your field of study, you might want to go for that. Now, the further ones here, the ones they call discussion problems, most of the time their answers are not in the back of the book. So you don't have to do any of these, but if you find some that are in the back of the book and you want to take a look at them and review those, that would be a legitimate thing to do. Okay? Just like to look through here just to see if there's any other things popping up here that I would see. Okay, now since we did finish chapter 1, now the clock is starting on the first test. And typically I give you at least a week to work on it, so that would mean next Wednesday would be the earliest I would expect to see it in. If you finish it sooner and want to turn it in, perfectly fine, but that gives you an opportunity to ask any questions on Monday. That's why I don't ever say you got to have it in before the end of the week or before midnight on Sunday night or something like that. I want you to be able to ask questions if there's something that's confusing or you can't quite figure out. Now, let me say this about that first test. Remember, all along I was saying a lot of the examples in the book were verify this, verify that, and it turned out that a lot of the test questions were verify this and verify that. And I thought they were going to be about as simple as the ones that we did in the chapter, because it's all from the same base. No, they weren't. Some of those are real bears. So hang with them. Remember how you eat a 5,000-pound elephant? One bite at a time. So take them one step at a time. Use as much paper, as much effort as it needs to work out the problems. Show your work as much as you can. Even if you wind up missing it, I can then give partial credit as much as I can. Now, if you need some more practices, again, this is chapter 1 in review. Answers to the selected odd number problems are in the back of your book. So if you want a few more to work on, number 1 should be back there. Number 3 should be back there. 5 should be back there. 7 through 11 should be back there. 13 should be back there. 15 should be back there. Excuse me. I've got hiccups. Sorry. Let's see. Yeah, 15 should be back there. Any of the odds 17 through 21 should be back there. Okay? And then either 23 or 25 should be back there. There's the 21. 23 or 25 should be back there. 27 or 29. 27 is at the bottom of this one. 29 was at the top of the next column. They should be back there. 31 or 33. That was on the second column here too. They should be back there. And 35 or 39. And there's 39. I'm sorry, 35 or 37 just above here, right up here. 35 or 37, and then 39. Okay, so any of those would be good if you want some more practice to do some of those type of exercises. The answers for those odds, or most of them, should be in the back of the book. They don't tend to have discussion questions here, so most of those answers should be back there. All right, any questions before we leave chapter 1 and go to chapter 2? Whoa! Why did it do that? I do not know. Okay. Now, scroll down just a little bit. Here is chapter 2. First order differential equations. Okay, remember we talked about order, type, always ordinary, and linearity. Okay, so in this chapter we'll be looking at chapter 2 only first order differential equations. We'll be looking at some that are linear, some that are not linear. We'll be looking at easy to solve ones and some that take a bit more effort. But as they always do, they start with a section here, section 2.1, solution curves without a solution, and that seems like sort of a contradictory type phraseology. But you'll see what they're talking about. It says here, the history of mathematics is rife with stories of persons who devoted much of their lives to solving equations, either algebraic equations at first and eventually differential equations, and we're going to get into that in sections 2.2 through 2.5. Separable equations, linear equations, exact equations, solutions by substitution, and at least one numerical method. Not the best, but just to give you an idea of what they're like. Okay? Those will be solving equations. This first section is just one of these general blah, blah, blah things that talk about things without really getting too specific. So let's hit that first, solution curves without a solution. Let's imagine for a moment we have in front of us a first order differential equation. dy dx is equal to some function of x